Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 5 on thermodynamic processes and cycles, and we've been looking at the Rankine cycle. And so far we're just looking at the basic Rankine cycle, and in our last video we talked about ways we might modify the pressures at various points in the cycle to maybe improve the thermal efficiency. In this video, we're going to be looking at an example where we do exactly that to our previous example problem. So in this example, we're going to have the company running a Rankine cycle. The water boiler is at 3 megapascals, which is the same as before, but now then an exit temperature will be 600 degrees C, and then the condenser will operate at 40 degrees C. So before we were only taking it to saturated vapor from the boiler, now then we're going to superheat it to 600 degrees C. That's the only change to the problem. Let's look at what the numbers say this time. So I have the data for state 1 and state 3. Now remember that we have assumed that the quality at the inlet to the pump is going to be a quality of 0, a saturated liquid coming out of the condenser and entering the pump. And so based on that, we have data for states 1 and 3. We are making the same assumptions as we did before, that the pump and the turbine are isentropic, and that the two heat transfer devices are isobaric. So we know, therefore, the pressure and the entropy at state 2 now, okay? And this time again, it's that saturated liquid vapor mixture. If we look up the quality by using the information that we have for saturated and liquid and vapor, we end up with quality of 0.903008. So what this has done is it has increased the quality coming out. Before it was 0.73, which I said was in the zone where we are going to end up with damage to our turbine if we operate that way. And now then we've brought it up above 90%. Not a lot above, but it is above. And if I look up and calculate the rest of these using the definition of quality, we end up with those. Now, what about state 4? Okay, 3 to 4 was our pump. We did that based on those calculations, based on assuming that the volume was constant, and then use that to back out from the first law the enthalpy at state 4. And so we calculate this information indirectly. It's a compressed liquid. It's hard to get good information for those particular states. Now let's calculate the work. Now these are going to be just like what we did before. And so the work for my pump is going to be 170.5 minus 167.5, so 3 kilojoules per kilogram. My work for my turbine is 2340.1 minus 3682.8, so negative 1342.7 kilojoules per kilogram. And just for the sake of reference, this was negative 875.4 kilojoules per kilogram. And so we've increased that number a lot. However, let's look at the boiler. boiler now requires 3,512.3 kilojoules per kilogram. And before it was not 8, okay, 2,632.7 kilojoules per kilogram. So we increased that one a lot also. And then the waste heat at the condenser is negative 2172.6 kilojoules per kilogram. If we then use this to calculate the thermal efficiency, my thermal efficiency is 0.3814, the net work over the net heat transfer. The maximum is the Carnot. It's going to be the same. 873. No, so it's actually gone up 0.6415. And the second law efficiency, the ratio of those two is 0.5946. Okay, so what's the story on this? This one, the thermal efficiency is better, right? So that sounds like we've done a great job. However, my Carnot efficiency is much larger, which means that overall our second law efficiency is much worse. We were around 85% before, now we're only 60% of the maximum possible. So we are not doing as good a job of using our resources with this design as we were with the earlier design. However, we have protected our turbine blades. So the other design really wasn't feasible. This is a better design from that standpoint, but we have done worse as far as efficiency goes. So that concludes this example. In our next video lesson, we're going to be looking at the same basic Rankine cycle, but we're going to add the effect of process efficiencies. So whereas this was for all reversible processes, we will look at something that actually is a much more realistic model of what you would find in a power plant. After that, we'll be looking at some other physical modifications to plants by changing out equipment and some other modifications to how we might create power plants. Thank you very much for your time.